Hello, I am Dinesh Kulkarni, a product manager on the ML team, and I'm really excited to share my team's work here. This is just the start of a journey. We have a lot planned, and we would love to take your feedback to shape the roadmap. Okay, so what are we showing here? We have a set of functions that aim to bridge the skills gap that's been talked about a lot, and it's very real. So whether you call it democratization or self-service for making these ML capabilities directly available, that is the goal of ML-powered functions. But there's also a shortage of time beyond the skills gap. Even those who have a data science team or are themselves data scientists often don't have the time for full-scale model building. MLPFs are meant to raise the level of abstraction and boost productivity. Simplicity of calling a SQL function with the power of ML models behind those functions is the crux of MLPFs. This is, of course, a part of the overall ML story in Snowflake. Our sister teams are enabling full-scale feature engineering with transformers and estimators, as well as full ML ops. But ML-powered functions are about taking some common jobs to be done and simplifying them down to a few functions. So what do these MLPFs do? Or what are they like? They are SQL functions. You can use them in a query just like you would use any other SQL functions. I could call it kind of the average and standard deviation taken to the extreme with ML behind it. There are no ops involved, typically just a method to train and one to infer, and the model is managed underneath the covers by Snowflake. They're thought through from an end-to-end perspective. They not only can be used for interactive exploration, they can be used in pipelines to get the streaming data to dashboard. So, for example, you could forecast or you could detect anomalies and have all of that happen within a pipeline. And that could be a pipeline built out of tasks, Airflow, dbt, whatever your choice. So what is the initial menu of functions? This is just a starting point. We have three of those: forecasting, anomaly detection, and contribution explorer. The first two are kind of well known, so I won't spend too much time describing them. But contribution explorer takes over where anomaly detection leaves. Once you have the anomalies in a time series, you can go to contribution explorer and say, hey, help me understand why that might have happened. And it'll go and figure out the different combinations of dimensions and tell you what could be the drivers that are contributing to the change in a given metric. You could use Contribution Explorer even without an anomaly just to manage the comparables. So you could say, what was the revenue last week compared to the same week last quarter or last year? So there's a whole set of possibilities that these functions enables. Now let's look at the demos to see how these actually work. First, we'll look at the data that we're going to use for this demo. The initial statements are just setting up the schema and database, but the third statement here is kind of interesting and worth calling out. You can have your account admin set this search path so that you don't have to refer to the fully qualified function name every time. All these functions are shared using the great data sharing capability in Snowflake that extends to functions as well. They're all in the Snowflake database in the ML schema, but you can just have that set up so that snowflake.ml is not a prefix that you need to type again. All right. So this data that I'm going to show you is generated by my colleague, Michelle Adar. It's a call support call data for a fictitious company that sells various phones and other products of that kind. Each call center customer support call is logged as a fact and can then be aggregated across country, call center, product, or by date or larger time periods like week or month. Customer support calls are a cost that many businesses need to forecast, detect anomalies in, and understand the contributions of various dimensions too. For example, if a new phone is causing problems, then you may need to improve self-service options or increase support staff training. So those are the kinds of business outcomes you can drive out of the forecasts and the anomalies and such. Now let's look at the forecasting functions, which is the focus of this screencast. These are in public preview as of June 2023 summit. So I'm going to scroll down. I'm not going to show this data in details about call center and straight go to the forecasting portion that uses this data. But before doing the forecast themselves, what we'll do is we'll see the generated data. So let's start by looking at the calls, what they look like. And this one is going to be just the basic facts here. Let's see the results. I see the timestamp for a call, what call center it went to, what group within the call center it went to, what product, in this case phone, does it refer to, how many weeks has it been since the launch of that product, and if that call had to be escalated or was answered by the first representative who took the call. So it's kind of the data. I can also show you how much data we have. It's all generated synthetic data, 640,000 facts. So not very large, but large enough for our basic needs. So let's look at forecasting. The first thing that I'm going to do is use a subset of the data to train a forecast model. Now, when we are forecasting, we're not interested in individual call. We're interested in some metric, and the metric here is number of calls every day. And so what I'm going to do is aggregate all the calls by date and see if I can forecast them. For now, I won't worry about what call center, etc. So let's see this. My view here is this, the calls for training. So that's done. I'm just taking calls from March 15th onwards. All right, so let's see the data that we've got here that we're going to train on. Very simple, just date and the number of total calls. That's it. All right, so let's build a model for it. Now, the way this works is we have a function to do the training that underneath uses Snowpark, which is our Python and Java and other extensibility capability. It uses a light GBM model plus polynomial regression and linear regression for trend and other things. And here you can use either a view or a table for training. So in this case, what I'm doing is using the calls for training view. I'm specifying that it's a view. And the two other things that I need to specify is what is the timestamp column. So that's a time series function. And then what is the metric, or what is the target that I have to aggregate and forecast on. So that's the one. All right, so let's create this model. And what I'm going to do is once that model is created, the next step, I'm going to show what models we have. Now I could just do the fully qualified one if I don't have my account admin who's already set that path. In my case, I did set it, but let's just go and look at these. So I've got a couple of models here. I run this demo script before, so I've got a couple of models, but the model that we just trained again was this calls forecast. And that one is the first one here. Now, if I don't, once I have the account admin set up the path, I can just do a show forecast and get that. So I don't need to type snowflake.ml every time. All right. So next one is obviously we want to do forecast. This time I'm going to do 30 periods, and these are daily periods. So for the next 30 days, I want to see the forecast. All right. So it's very simple. I trained the calls forecast model. Remember, that's the model that I had here. And off of that model, I'm going to drive a forecast. So the function is forecast and takes in how many, at the simplest level, takes in just the number of periods you want to forecast for. All right, so we'll do this one. And as it's running, I want to point out a few more things here. So let's look at that. All right, so you've got a timestamp, you've got a forecast, and we also have lower and upper bounds. And these bounds are based on what we call a prediction interval. A prediction interval is what are the chances that the forecast lies within those bounds. And the default here is 0.95. And so with a 95% probability, this forecast lies between the lower and upper bounds. So that's the gist of it. Now let's see in a chart what this looks like. So first, let's take this one. What it does is it shows the lower bound, the upper bound, the forecast, and what it's unioning is the initial calls for training part with the actual forecast. And that's the forecast produced by the stored procedure here, the forecast stored procedure. And it's looking at the results of the last query and unioning them. Because remember, we have the data from the original one and then the forecast. Now in the first, for the original data, there is no forecast or lower or upper bound. And as we get to the lower ones, there is no actual because this is future. And it's got a forecast, a lower bound, and an upper bound. So that's what we have. All right, so actually let's do one more thing. Let's see what the chart looks like here. And what I'm going to do is make a few changes here. I don't want to just have forecast. I also want the actuals. And what I'm going to do is just clean this up a little bit so I can see the forecast properly. All right, so what I have here is a chart. These are the calls, is the actual data that's in blue. Up to this point, it's actual. And then starts the forecast time series. You can see that there's a certain trend, and let's make this a little bit bigger. So there's a certain trend here, which is weekly cadence. So that's the seasonality. Every week it rises up first and then, it rises up first and then drops down towards the weekend and so on. And so that's the seasonality. There's also a downward trend, which is great for the business because it's a cost. And then our forecast respects both the seasonality and the trend here. So these are the kinds of things that it covers. We obviously benchmark this against other potential algorithms like AutoETS or Facebook's Profit or Arima. And based on all those analysis and so on, we found the best trade-off here with LightGBM to do good forecasting along with low cost of prediction. All right, so what we can do here is also see what is the forecast. So we can actually run it with a different prediction interval. If you so choose, you can override the 0.95 default and specify an explicit interval. Now remember, if you want a high probability that the readings falls between the intervals, you are going to need to provide a wider prediction interval, or you're going to get a wider range between the lower bound and the upper bound. So I can do this. Instead of doing the forecast, it's the same model, but I'm doing it with a different prediction interval. And now if I see that, I can, once it runs, I don't want to see the chart. I want to see the results. I can see the lower and upper bounds, and we won't go and compare those, but these are wider bounds because I specified 0.99 as the, or 0.999 as the prediction interval. All right, so this is just a starting point, but let's now look at the feature importance. So this is another capability that's built in. You can say, hey, tell me what is the importance of these features. Now, in this particular case, all we have is what we call endogenous features, which means they're part of the time series. So that is the 0.66. The day matters because that's the one driving seasonality. The epoch time, is the third one, and so on. So you can see how this works. Here we don't have exogenous variables, but if I had some exogenous variables, and I'll give you a quick example. Imagine there were some external things happening, such as product promotions or something that are announced by the manufacturer or so. You can imagine that more of a particular product sells. If you sell more of the product, you might get more calls for that product. And so that kind of a marketing promotion could be an exogenous feature that could be factored in. We don't have that in this data. I won't go through that. But in that case, this feature importance will show you how much that counts towards the forecast. All right, so next one. Right now, what we did was we aggregated across all call centers, all products, etc., and created a daily time series. I could have, instead of doing that, kept let's say the product here. And so what I've done here is I've created a different view that keeps the product intact, and so it's a per product kind of time series. So let's create that view and use that. All right, so what I'm going to do next is just use this one, and we'll see what this does. So here I can specify the series column name, which is product. I didn't have this before. If I scroll up here, I can show you that I did not have a series time name. There's a single series, but I could have multiple of these and do the prediction in one fell swoop for each product or each country or each call center or whatever I want to have as an additional dimension. All right, so once I have this one, I can do a forecast similar to the past, how I did that. So let's see what it does. This is exactly the same as this forecast function, the forecast store procedure, calling it for 30 units or 30 days, and same here, 30 days. And what I see here is same sort of forecast, but this time I see the series name as well. So I can see it for this +2 or S22 or Galaxy 7 or whatever, Pixel 6a, whatever the phone is, whatever the product is. Now, the interesting thing is that these functions are not just for the interactive work that I'm showing you right now. They also work beautifully in data pipelines. And the reason why they work beautifully is we also have the concept of streams that give you just the incremental data. So let's say I want to do this forecast every day. So in this case, in fact, what I'm doing is I have a certain schedule, but this is for training. So I can adjust how often I do training and how often I do prediction or inference with it. So in this case, this is for training. I run it every Sunday at 1 a.m. PT or something. And you'll notice that here, it's very similar, create or replace this forecast. So this is the model training. And all I've done is wrapped it in a task, and it works beautifully as it is. Now, of course, we won't wait for Sunday 1 a.m. PT here. You'll have to just trust me, or you can try it on your own since this is available in public preview to you. So you can just go ahead and try that out. I can similarly have a separate one for doing inference. Now, this one shows a very small kind of mock pipeline. I have a step that does the metric calculation, howsoever it does it. Let's say the metric is how many calls were there for the last day. And now, in addition to that, I can also do a forecast looking 7 days ahead. And so I can keep updating this on my dashboard. So along with showing how many calls happened yesterday or over the last month daily, I can also show what is the forecast for the next 7 days, etc. So you can just make this a part of your normal business process without any additional work. We manage the model here for you. We create the model, manage it under the covers. We provide explanation. You can do the inference, and then you can do the training and inference on whatever cadence that makes sense for you, either interactively or in a pipeline. All right, so here we'll see how to detect anomalies using the built-in functions. Let's look at the data first so we get a sense of what the information looks like. I've got date and the total number of calls. Again, just to recap, this is about a fictitious company that's tracking its call center cost, total number of support calls coming in, how they're resolved, etc. So that's the time series, a particular date and the total number of calls on that date. We'll now build a model for anomaly detection. And while it's running, let me show you a few things. What it does is the same thing as forecasting, uses a reference to the view, calls history. I could have put a query reference instead of view here as well, or a table reference. If I wanted to, it points out what the timestamp column is for the time series and the target column name, the one that we're going to detect anomalies in. And I'm leaving the label column name empty because this is unsupervised. What is happening here is that I'm not explicitly labeling the row as anomalous or not. And the reason for that is we can use the forecasting technique and find out which points are beyond what we would have forecast the value to be. So that's what we're going to do here. So this has been trained, and now let's see what models we have. As I had shown before with forecasting in the previous episode, I can do directly show anomaly detection instead of the show snowflake.ml.anomaly detection, the full reference here, because I had set, or the account admin had set the path previously. All right, so I've got a couple of models here that are ready to go, including the one that I just trained here. You can see the date. It's August 8th, and so let's go and use that. We're going to now do inference using this model, and as before, while it's running, let me show you how we do that. Same thing again, I'm using a reference to the view, could have used a query as well, timestamp and total calls. So fairly straightforward. So let's see what the inference looks like. So there is the timestamp, the series Y, or what the total number of calls, what the forecast was, the lower and upper bounds for the forecast, and is this an anomaly? And the reason is the 6580 is beyond the highest value of the upper bound of here. Or sorry, rather it's lower than the lower bound, 6589 and 6580. And so it is marked as an anomaly. And then I get a few extra pieces of information, such as distance from what you would have expected it to be, what percentile it is in. It's a very low sort of percentile. So a few things that I can use to filter out the anomalies further. All right, so that was unsupervised training and inference because I hadn't provided any explicit guidance as to which rows are anomalous. Is this particular day bad or it's not bad? We don't know. So that's what it is. But one more thing maybe worth seeing is we can see the chart and see what the calls look like. Here's the normal trend. I've got weekly trend here and sort of some, flattish or whatever kind of trend. And then suddenly I see the calls shoot up and so on. So there are kind of injected anomalies in this synthetic data. And that's why you see all of these things. All right, so let's move to supervised anomaly detection training. Now, in this case, what I'm going to do is use a variant of the data in a different table called labeled calls instead of the unlabeled calls. So let's see what I have here. The results here are, I've got date, total calls, and a label that says, is this an anomaly or not? So somebody has to provide that information if you want supervised one. So let's see what information I've provided. Mostly it's all false, and then suddenly you'll see that certain cases, I see a true here, a few true values here, and so on. So a bunch of anomalies that are sort of clustered here. Oh, and I could also show you the chart for what looks anomalous. You can see that suddenly there's a spike here, so that's anomalous. There's a dip here that's a little bit anomalous, etc. Another dip here. So I've marked these as anomalies, and the rest is all normal. All right, so with that training data in hand, I'm going to do this training. I'll first start running the training job and show you what we are doing here. Instead of view here, I'm using a table called labeled calls because I added that label column. As before, the timestamp and the target column, but I've now added a label column name for anomaly marking, and this is what is going to be used as the training data. Instead of doing the usual, hey, is this within the forecast band or not, this time it's going to just use the explicit label. All right, so now that we have that trained, we can click the results here. Yes, we have the model successfully created, so I can go use that for inference. While we are doing that, let me show you one more little thing here, which is I'm deliberately setting the prediction interval here. And the prediction interval is the probability that the value is within the upper and lower bounds. And so in this case of inference, I'm saying I want that value to be within this bounds with 4/9 level of probability. So if I say 4/9 of probability, that means the very wide band. That means I'll have only a few anomalies. So let's see how many anomalies I have based on the training data. Let's run that. Oh, I've got 13 anomalies here. And next time what I'm going to do is use the same exact model, but instead of doing, so let's do the inference and let me show you what the call says here, which is different. Now it's using view, calls for detection, and instead of the prediction interval being 0.999 like before, it is now set to 0.95. So a much lower one, which means I don't need the probability to be too high, which means my band between the sandwich that you get, the upper and lower values, they're tighter now because I can afford to miss them. Now, if I have tighter band, what's going to happen is anything that's outside that is an anomaly. So I'll have more anomalies. So let's see if that's actually true. All right, so I've got 17. Earlier I had 13. Now I've got 17 anomalies because I dialed down the prediction interval. All right, so that was just anomaly detection in a nutshell. I do training and inference for either of them. I can basically use the prediction interval if I want to. If I don't, that's fine. Supervised, unsupervised, both are available. But the interesting part is that this is usually not about interactive usage. You need anomaly detection to run in the background 24/7 or on whatever frequency you choose so that you're alerted about the anomalies. So let's see how that would work. We're not going to go through and send emails, but let me show you the code, what it would look like. So in this case, what I'm doing is I've got a little stored procedure that I can run on a regular basis. And within that, I do the prediction or the inference of anomalies, so detect anomalies. Once I do the detection of anomalies, then if anomaly count is greater than 0, I want an alert to be sent. And the way this works is I use the built-in function system$send email, fill in some piece of information. In this case, it's going to this fictitious address oncall@snowflake.com. Please don't try that. It won't work. But that's the email address I'm using. And then I can provide notification on anomalies with a message that I want. So you can take a look at what anomalies have been detected by the function and then selectively potentially send out alerts if you like. In certain cases, you could just log the information and whoever is on call can look at it during business hours. But if the anomaly is very large, so for example, if you've set the prediction interval to be large and so you'll get fewer anomalies, those might be more severe. And in those cases, you might want to send out an alert. And that's this example. So this can run in your normal data pipeline. All right, so let's start with Contribution Explorer and what it looks like. In the first part, we're going to see the UI. Now, the Contribution Explorer function itself is in public preview, but the UI is still taking shape. It's in a private preview. So if you want access to that, please talk to your account team, the Snowflake account team, and they'll help you get access to it. All right, so let's see what it looks like. I've enabled this account for queries for the UI. And I've got this basic data, call center data with product and total calls. Let's see what it looks like on a chart. So I've got this weekly trend goes up midweek, comes down on the weekend, etc. And then I've got a trend which is downward. And then suddenly I've got some anomalous behavior right here. And what I'm going to do is use Contribution Explorer to understand why I'm seeing this kind of increase here. Now, the interesting thing about Contribution Explorer is that it picks up where anomaly detection leaves off. In the previous episode, I showed how you can use anomaly detection ML-powered functions to find out anomalous rows. And here we're going to take that forward further and see what the contributors are. All right, so let's do the basic things required to see the contribution. So first thing I'm going to do is mark the area that is interesting. We call this the test period. And test period means this is the one we want to focus in on. But we can't just understand what's going on in the test period without having some frame of reference, some baseline. And that baseline is the control group. As in any statistical comparison between A and B, one of them is test or treatment group, and the other one is the control group. And the control group is sort of the normal one. So here, this is my entire control group. So now that I've marked both of these, and all of this was possible because I turned on Contribution Explorer. So once you're signed up for the private preview, you'll see this added to your UI. You can turn it on if it's not already on, and then mark the sections for test and control. All right, so I've got those marked. This is exactly the metric. I want to see why the calls are higher. The date is the timestamp column. And now comes the next interesting part, which is in the query. And let's go back to the query and see the query again. So I've got in this query a number of dimensions. I've only picked a couple here, call center and product. And I'm going to restrict to that. I could have put many other dimensions, but these are the dimensions that will be analyzed to find out which ones are disproportionately contributing to the increase, or in other cases, it might be a decrease. And so I want to call out those dimensions because those are the ones I want analyzed. So you'll see that there's a Run Contribution Explorer and it's not ready yet because I haven't picked dimensions. So I'm going to do that now. So the dimension I'm going to pick are the ones I want both. I could pick only one or both, but I'm going to pick, let's actually just only pick one first. So in the add dimensions, I'm going to, all right, so that's, we've got two dimensions, that's fine. We'll go and run this and then I'll show you what the results look like. So what it's going to go through and do is that it's going to analyze the different combinations, and there can be a large number of them, and then come back and say what is contributing the most. So product equal to other, which means it's not in one of the well-defined categories like iPhone or Pixel 6a or whatever, and that is causing the most calls here. And it is so disproportionate that you would have expected only 4,328 or so calls, but instead what you're seeing are 32. I mean, this is like much higher number here. So that's a very large contributor there. And so it's a very big surprise that we didn't expect it to contribute so many, but it is. Similarly, call center Texas, product equal to other has, so if you even dive down further beyond the product equal to other, you'll see more surprises, and those are bubbled up. All right, so I'm going to close these results and go back to code, because next what I'm going to do is I'm going to show you how to use the underlying function that the UI calls. So you don't need the UI necessarily. You can use the same query, which is this one, call center and product, and some call count. And so that's what I'm going to do here. So the query here is again very similar. So in this case, instead of doing it through UI, I've used these as dimensions. So that's my dimensional categorical dimensions input. There are no continuous dimensions here. There's nothing here that is going to change the result based on something continuous like sales or something that doesn't have few discrete values. And what I have here is I've done the marking of the control and test groups through this mechanism. So if the date is between this period, this is what I did graphically in the UI. Now I've done this in a query and I've marked them as labeled. So one of them is control, one of them is test. And then the metric is call count as before. So same basic query. And now with that query, so that all that query is here, what I do is I'll call snowflake.ml.topInsights. So that's the function underneath. It takes in categorical and continuous dimensions, the metric, and the input label, which is the control versus test group. So let me run this query. Once that query is run, let's see, we can go into results. I don't want to see. So that view has been created. Now what I'm going to do is just go into it and see what the change contributors are. And I'll get a lot more detailed view of what it is. So here is what is the insight? Each insight is essentially some combination of dimensions. So root means everything. And this is my baseline. What changed at the root level? So at the root level, there's no surprise, there's no excess. This is the change. And the change is I've got a KPI test and control. Remember the test and control groups. And this is the difference between the two. Now, the number of days is unequal in the two, which is fine. We make sure that we scale it appropriately and look at the differences. And then in each of these cases, it says, oh, okay, this is the difference. This is what is the highest. This is what is the lowest. And I could, if I wanted to, sort it by whatever that I care about and then see the changes. So I can go back here and I can say order by. And here, let's see. I don't want surprise. I want change order by. In fact, let's go and see what we can do here. So we've got a whole bunch of differences. I could do a relative change. I could do growth rate or excess and so on. So what I'm going to pick is the relative change here. So order by relative change. And I want it to be descending. So the highest one comes up first. So let's go do that. And now we'll see the output that is ordered by the relative change. The highest change is in a particular combination of dimensions. This is the call center, France, Tech 1, etc. So I can see which ones have the highest contribution to this. So we just saw how to do it through UI or through the function. You can use this when you're trying to do root cause analysis on an anomaly, or you can just use it for comparables. So for example, some internal groups in Snowflake already use it on a daily basis. They'll compare, okay, how were the revenues or how were certain other metrics on the same day last month or same day last quarter, same day last year, whatever their comparisons are. So you don't even need an anomaly. You can just go and say, tell me more about it. Tell me a story about why I'm seeing the number that I'm seeing. And it'll go and do the data mining and bring out what we call gems and show you the gem is this. And the gem is all about surprises. What is more surprising? If something is growing at trend, that's not a surprise. Something is not growing at trend or declining when everything else is growing, that's a surprise that needs to be bubbled up. So that's what Contribution Explorer does. Thank you for joining us.